Strawberry is native to Chile and is a perennial strawberry plant in the Rosaceae fragaria genus. The fruit is soft and juicy, rich in fragrance and nutrition. It is deeply loved by consumers and has a broad market prospect. However, a suitable environment also creates good living surroundings for pests, resulting in new yellow leaves. Besides, excessive green leaves and white flowers will also cause poor quality and quantity of strawberry fruits. Therefore, it is really important to detect unhealthy and excessive leaves and flowers in time. In the ASABE student robotic competition, our slide consists of a brown bottom plate and 2 wooden seat beds. There are 2 mirror tracks on the field, and we need to start from either track to complete a non-tracking navigation. Each seedbed has 12 simulated plants and 1 real plant. On each plant, green leaves, yellow leaves, and white flowers may appear. The green leaves are also subdivided into 4 different shades of green. Our task is to identify the number of yellow leaves and white flowers of each plant and upload them to the software interface through the network. With such a difficult visual recognition challenge, we first used deep learning to solve this problem. The YOLOV5 algorithm can complete a recognition task of this competition well. However, it would take 3 seconds for each image. We finally gave up this approach and adopted OpenCV method to speed up this task. In this picture, in order to identify the stem, we separate RGB channels around the center of the plant and then use the Gaussian filtering to get the direction of the stem. Then for each stem, we fit a path based on the color and climb in that direction to find the end of the stem. We take a small area a little farther from the end, judge its color to exclude green leaves, and distinguish white flowers from yellow leaves based on the size of the connected domain. As the mechanism changes, we take pictures from the bottom up. The previous identification method is still effective, but the challenge we face is that the stem will block some parts of the flowers and leaves. In order to solve this problem, we use 2 cameras to eliminate blind spots, and use coordinate projection to prevent repeated recognition. As a result, as long as the camera finds a target, we can recognize it. Before, we used the Raspberry Pi to recognize and used Arduino to control the robot's movements. When our mechanical structure was simplified, we used Raspberry Pi 4B as the only controller. To complete the task of driving without guidelines, our strategy is to use the plant bed as a reference for navigation and go straight forward. We have tried to use infrared sensors and ultrasonic sensors to ensure a certain distance between the car and the plant bed. But this adjustment method has a certain hysteresis. Therefore, we choose contact switches to let the car work along the seatbed to ensure the stability of driving, and use the steering gear to control the forward direction. In order to reduce the amount of calculation, our robots would only take photos and identify when it is facing the plant directly. So it needs to identify the plant base. We chose a laser sensor that is more accurate and less affected by the environment. Since the 2 tracks are mirrored and our robot needs to be able to work in each track, we placed an infrared sensor behind the car and used the information of whether it detected the wall to determine which direction to start. We used to use ESP8266 for wireless communication. After realizing the Wi-Fi communication of the Raspberry Pi, we gave up the module to reduce costs. The first generation robot was designed to use a mechanical arm with a single rotary joint to control the ascent of the camera. Its mechanical structure is very simple, but it has high requirements on the accuracy and quality of the steering gear. Therefore, on this basis, we have updated and integrated a second generation robot which uses a rack and pinion to push the camera up at a constant speed. It can not only ensure robot to complete the positioning of the camera accurately and stably, but also make sure the motor working within a safe working range. However, to complete the task of identifying flowers and leaves, this design occupies a huge volume and quality, and we didn't think it was necessary. So we tried to observe the plants below. It brings us lower production costs. In actual production environment, it can also use the ultra small size to shadow through the large plant's growth environment to work. Besides, we used the track wheels before. And now we use the helical gear transmission structure to reduce the number of motors and the weight of the vehicle. This idea has grown as a result of our step-by-step exploration. In the end, a recognition car of the size of a pound was born. Now we are weighing the robot, and it weighs only 1.2 kilograms, so as to say 2.64 pounds. The total cost of our final robot is $104.68, and the price of the computational devices is $55. In the initial test, we found out that the strong light source above will affect the recognition. So we use a free retractable umbrella to improve the recognition effect of our robot car. Considering the security, we have prepared a start button and an emergency stop button which can fully shut down the entire system at any time. Both are easily accessible. Let's move on to the display of the final version. We randomly generated a result according to the provided GUI program, and then we used it to set the simulated strawberry plant. We also measured its volume, which is very small, about 7.3 inches in length, 6.2 inches in width, and 7.2 inches in height.
3, 2, 1, start!
During operation, the recognition results can also be displayed on the TFT display screen in real time through Protocol SPI, so as to facilitate the debugging of the robot and improve the external expressiveness of the robot.
Stop!
In this test, we got completely correct results. This is the pictures of the recognition result of this test. As you can see from this picture, white flowers and yellow leaves can be well identified. And here we can see that even if some targets are blocked in one perspective, we can still recognize it from another one. In general, our robot has the characteristics of small mass and volume, fast recognition, low cost, and high accuracy. We also make a trial to use UAV to validate the feasibility in this situation. As you can see, it performs excellently. Even there was a breeze produced by itself during our identification. Benefit from the built-in HD camera, even an extremely small white flower is identified accurately in the follow-up video processing. So that means we can expect UAVs to play an important role in this domain. As more and more laboratories try to use UAV to get agricultural information, we believe that we can use UAV to accomplish agricultural applications such as illness detection, crop yield monitoring, crop yield forecasting, agricultural land use monitoring, and so on in the near future. We come from Agricultural Robot Club of Zhejiang University. Our instructor is Mr. Ye, who majors in agriculture electrification and automation. Our captain Xin Yang is responsible for circuit design and video editing. The team member Yu Fanzhou realized the programming and debugging of the robot. Team member Fang Hao Wang completed the robot's visual design. Team member Xue Fan Wang realized the design of the overall robot mechanical structure. Team member Fang Wu was responsible for financial reimbursement. Team member Yi Zhou contributes to art design. Finally, we are very grateful to the ASABE organization for overcoming all kinds of difficulties to hold this online competition. This gives our team an opportunity to cooperate and learn from each other and left an unforgettable memory. Let us work together to continuously promote the development of agriculture. Thank you for watching.